Alright, so in this video we're going to look at a more practical example that actually is found in electromagnetism. So basically we're giving some electric field that only depends on the radial distance from this thin wire. So basically the vector field for the electric field is represented as follows. We have some radius r, which is the distance from the center axis, and then everything else is a constant. So lambda is a constant, pi and epsilon are constants. So the idea is to compute the flux across the entire closed cylinder. So we have a surface at the top S1, a cylindrical wall S2, and then a surface at the bottom S3. So we know that the total flux integral for this closed surface, this is what that circle means, it's a closed surface, is going to be the addition of all, or the sum of all those surface integral of those flux integrals. So what we're going to do in this case is we're going to split it up into three surfaces. So we're going to start with S1. So we notice that this surface is going to be, so this I should probably specify that this is the Z axis. And then basically what we have is we have our Z axis here. And then we have a surface that is basically just completely flat. So what this means is that we have a normal vector, right, that is always going to be the same for any point on this surface. The normal vector is always going to point along the Z direction. So that means that we can write n equals to 0, 0, 1. Now what's going to happen is if we want to compute the flux integral across surface 1 of E, then you know from the last video that we can represent this in terms of the normal vector to that surface. So we can write E dot product with the normal vector times some magnitude of the surface ds. So now it all boils down to calculating this term. So if we have E dot product with the unit vector n, then what we're going to have is the following. We can have lambda 2 pi epsilon 0 r 0, 0, and then dot product with 0, 0, 1. And what you notice here is that this is actually just going to be equal to 0. So if this dot product is 0, that means that the entire flux across this first surface is just going to be equal to 0. So we didn't even need to set up any integral. We already know it's 0 just from the properties of this. So now let's compute it across surface 3. So surface 3 is just the same, but it is now pointing downwards. So we have our surface that is basically pointing down like that. So this is the Z axis. So now we have a unit normal vector that's going down, and you know it's because this is a flat surface, the unit normal vector is always pointing along the Z direction but in the opposite direction. So in this case n is going to be equal to 0, 0, minus 1. Because remember, the unit normal vector is always pointing away from the surface. So in this case it is going to be pointing down. So if we take the dot product of E with n, then once again we're going to get 0, which implies that the flux integral across the surface 3 is also going to be 0. So already we found two flux integrals very quickly without having to do any integration. So this is one of the really nice properties of knowing how those normal vectors work. Now for surface 2 we have a cylindrical wall. So let me just draw it here. You have your Z axis, and now you have a cylindrical wall. It is open, so basically you have this. So now let's have a look at what the normal vector is pointing. So at any point here, the normal vector to this surface is going to be pointing away like that. So basically we're going to have normal vector here, normal vector there. And then this one is going to be coming in here. And then it just keeps going. So it basically is just pointing away from the cylindrical wall at any point. And now if you notice, basically at any point on this surface, the normal unit normal vector to that surface is always going to be pointing in the direction of r. So if we are using cylindrical coordinates, basically we're using the coordinate system r, theta, and z, if these are the basis vectors of our coordinate system, and then n is just going to be pointing always along this direction, which is the radial direction, and then that's it, that's all it is. So in this case, our unit normal vector to the surface is just going to be equal to 1 and then 0, 0. So now if we go and take the dot product with the electric field, we're going to have, well, we have this times 1 in this case, so that's going to be, actually this is not going to be a vector, this is going to be a scalar. So we have lambda over 2 pi epsilon 0 r, okay, and now we're gonna have everything else is just going to be 0. So this is going to be what we integrate here. Alright, so now in this case we do need to set up the integral. So the flux integral for this surface 2 is going to be equal to this, which is equal to that E dot product with unit normal vector ds as 2, and now we have lambda 2 pi epsilon 0 r ds. Now the one thing that we notice is that the radius here is always constant because the radius is always 1, so it doesn't really change, which means that this is just going to be a constant in this particular case. We know that everything else is a constant, so we can easily take everything out of the integral, and we can rewrite this as 2 pi epsilon 0 r, then flux integral. So this is actually just going to be a surface integral here. But now we notice, well, hang on a minute, this is just going to be the surface area of this whole cylinder. So we know that if we actually open this cylinder and we just extend it like that, we know what the circumference is going to be. The circumference is just going to be, the radius is constant r, so we have 2 pi r, that's the circumference, and then the total height was given as h, so the surface area is just going to be h times that. So that means that this flux integral is going to turn out to be 2 lambda over 2 pi epsilon 0 r times the surface area, which is 2 pi r h, and then what's going to happen is this, and this and that are going to cancel out. So in the end, we're just going to have lambda times h over epsilon 0. So as it turns out, for this particular problem, our total flux integral for the closed surface is just going to be a constant value. So it is only going to depend on the height of the cylinder, and then lambda could be just a charge distribution across the wire, and then this is just a constant. So this is our final answer. And what that means is that if you have an electric field which is basically just radially going outwards from that thin wire, then of course you should expect that on this cylinder this is going to be the flux, the electric flux going through it. And we actually found that without having to do any integration. We just used some of the knowledge we have of flux integrals to actually solve this problem.